The F-35B is arguably the most advanced plane ever made, a jack of all trades, a stealth fighter plane combining and improving on the capabilities of the F-16, AV-8B Harrier, and B-2, a highly maneuverable fighter plane capable of attacking both airborne and ground-based targets. A stealth fighter taking the lessons learned from Lockheed's previous ventures into stealth with the F-22 Raptor and F-117 Nighthawk. A plane fitted with the most advanced sensors and computer systems, sharing information almost instantly with allies without compromising stealth, and presenting the information directly on a heads-up display on the pilot's helmet visor, giving unparalleled situational awareness, allowing a flight of F-35s to effectively fight as a hive mind. Perhaps most boldly of all, the F-35B is capable of transitioning from horizontal to vertical flight with a push of a button, using directional thrust and a massive vertical turbofan engine hidden within the plane's body, making it possible to land like a helicopter on the relatively small amphibious assault ships of the U.S. Marines. Fitting all these capabilities into a single airframe is an extremely difficult task. Designing for stealth demands careful molding of the exterior of the plane, dictating the design of crucial features, creating unavoidable trade-offs. There are a lot of misconceptions about stealth. The goal isn't to make an aircraft invisible. It will be detectable. The goal is to delay enemy detection for as long as possible. For bomber aircraft, it shrinks the range of the enemy's radar stations, potentially opening gaps in radar defenses and allowing the aircraft to slip through undetected. For fighter aircraft, it provides a critical advantage: detect your enemy before they detect you. To gain these advantages, we need to make it harder for the radar receiver to decipher whether the return signal is just background noise or an enemy aircraft. To do that, we need to minimize the strength of the return signal. There are several mechanisms for a radar wave to be reflected. The most significant and most obvious way is through specular return, otherwise known as regular reflection, like a mirror. 1. Where the angle of reflection equals the angle of incidence. We want to avoid large flat surfaces that could reflect straight back to the radar receiver. Corner reflectors, W, where two surfaces set at a 90-degree angle to each other, need to be avoided at all costs. Tailplanes, consisting of the vertical and horizontal stabilizer, are the perfect surfaces to create a corner reflector, allowing radar to bounce off both surfaces and return right back in the direction it came. The best way to avoid this is to remove the tail completely, like the B-2, but this impacts maneuverability greatly. Instead, we can replace both the horizontal and vertical stabilizer with a V-tail, as seen on the F-117 Nighthawk. The V-tail can act as both a rudder and an elevator, and we can see how by examining the resultant force generated when the control surfaces are actuated to different positions. We can actuate them in opposite directions to generate a horizontal resultant force, providing yaw control as a vertical rudder would, or we can deflect them in the same direction to provide pitch control as an horizontal elevator would. This configuration is sometimes used for unique-looking aircraft like the Cirrus SF-50, allowing it to mount a single tiny jet engine on top of the fuselage with its exhaust directed straight through the V-tail. A private jet so tiny and lightweight that it can deploy a parachute to rescue itself in emergencies, having rudder and elevator controls linked in a single mechanism like this is not ideal. Fighter jets like the F-35 and the F-22 need superior control authority, and that is a function of control surface area. The larger the elevator, the larger the pitch control. If a control surface is working a double role, where rudder and elevator action is needed at the same time, it reduces the control authority. So, both planes also feature large elevators, offset by a distance and angled to prevent corner reflections. We can see many more trade-offs in design by comparing the F-117 and F-35 in the quest to fulfill both stealth and fighter requirements. Both the F-117 and B-2 have their engine air intakes mounted on the upper surface of the plane, which prevents ground-based radar from bouncing around inside the intake and back to the receiver and helps reduce infrared heat signatures. However, for a plane expected to make high angle of attack maneuvers in life and death situations, this isn't a design you would want to include while performing a maneuver like this. The air intake will receive lower pressure air, which will lower performance right when performance is needed most. Air intakes located underneath the aircraft, like the F-16, will cause too much radar return, so twin intakes located on either side of the fuselage are instead chosen. The air intake has some clever aerodynamic features too. This seemingly innocuous bump plays an important role. This is aeronautical engineering epitomized. Every seemingly insignificant design feature has a purpose. Mounting engine intakes along the body of an aircraft comes with some issues that pylon-mounted engines avoid. As air travels along the length of the body, air begins to form a layer of slow-moving turbulent air called a boundary layer. If this air is allowed to enter the engine, it not only lowers performance, it can also damage the engine. As the turbine rotates, it will pass through the slow boundary air on one side and then fast free-stream air on the other. This means the force on the turbine blade changes for each and every rotation, causing cyclical bending, a recipe for fatigue failure. Planes like the F-16 feature a boundary layer diverter that separates the inlet from the fuselage with a small gap, but this design increases radar cross-section and increases drag. 2. Later variants of the F-16 tested the DSI, a diverterless supersonic inlet, essentially a large bump that creates a region of compression that pushes the boundary layer away from the inlet while also scattering incoming radar and lowering drag. The test flight demonstrated it could meet performance requirements, ushering its introduction to the F-35. The final product reduces weight by 30% and lowers production and maintenance costs. Moving down the plane, we can see other hints of stealth design. Long, sharp edges are the enemy of stealth. Sharp edges cause radar waves to scatter in all directions. Radar can even travel along the length of a surface in the form of a traveling wave, and then scatter upon reaching the trailing edge. The strength of that return signal can be reduced with a few clever techniques. The strength of the signal will depend on the length of the edge, so the first technique is to reduce the edge length with serration. You can see this technique very clearly on the trailing edges of the B-2. However, it's less obvious where it's used for the F-35 until you start looking at all the access hatches hidden around the aircraft. Every single unavoidable surface gap on the aircraft has a serrated edge. This hatch opens to reveal a telescoping ladder to allow pilots to climb in and out of the aircraft. These open to reveal the landing gear. These are the internal weapons bays, essential for keeping the radar reflecting missiles hidden from view, and these smaller hatches are flare dispenser doors. Flares are effective decoys for heat-seeking missiles, but they do nothing to prevent radar-guided missiles. In the face of radar-guided missile proliferation and continued growing sophistication in the technology, a new decoy system was developed. This new technology is released from this panel. When needed, this access door opens and a transmitter begins to reel out to a safe distance behind the plane. It has 3 levels of countermeasures to protect the F-35 from attack. First, it actively jams missiles while they attempt to lock onto their target by emitting jamming signals which the onboard computer computes and delivers to the emitter through the fiber optic tow line. If the radar manages to obtain a lock, it then begins to attempt to break the lock, disrupting the tracking algorithms guiding the missile towards its target. Finally, if all is lost and the missile is bearing in on the aircraft, the emitter begins to simulate the aircraft's radar signature, drawing the missile towards it as a decoy. 3. These serrated hatches hid critical components of the F-35, but more can be done to reduce edge scattering in these locations. You may notice that the color around these edges is different to the rest of the plane. This is because the edges are treated with a special radar scattering tape. In the same way traveling waves scatter when they meet an edge discontinuity, they will scatter when traveling over a change in conductivity. The F-35 uses this to its advantage to scatter the waves over a longer distance, reducing the return signal by spreading it out. The tape has a conductivity gradient gradually, decreasing its electrical conductivity, causing radar waves to scatter at each interval, slowly decreasing the intensity of the surface wave before it reaches the edge where it would have released one large return if the tape was not present. The surface of the plane itself is composed of specialized radar-absorbing material. In 2010, Lockheed Martin filed this patent for a carbon nanotube-infused composite material that can absorb radar waves from 0.1 MHz through to the 60 GHz. This is an incredibly wide range of frequencies, notably covering the frequencies Russian surface-to-air missiles like the advanced S-400 system uses. The effect traveling surface waves have on stealth design can be seen elsewhere. You would imagine a cylinder would great way to scatter radar in all directions, lowering the strength of the return signal, but if a radar wave comes in tangentially to a cylinder, and the wavelength is at least 1/10 the cylinder's circumference, the wave can actually travel around the outside of the cylinder and travel straight back to the receiver. 3. This is likely why the F-35 features this sharp edge breaking up the circular nose cone. Where the F-16 has a nearly perfect circular nose cone, the F-35 features a ridge. The largest hatch on the plane is strangely not serrated, and this is for good reason. This hatch hides the powerful lift fan within. The airflow in and out of this lift fan needed careful consideration. The lift fan is essentially a tiny helicopter capable of generating 85 knots of vertical thrust, and in doing so it creates a lower pressure zone above the plane, violently sucking air into the aircraft at a 90-degree angle. This air has to travel over the hood to reach the inlet, and thus the hood needs to allow air to smoothly pass over it without creating too much turbulent flow, which would lower the performance of the lift fan. This is why the inlet door is not serrated, as the sharp edges would cause distortions in the flow. This hood alone went through several design iterations to optimize the airflow flowing by it. The demonstration X-35 aircraft had 2 doors opening towards the side of the aircraft, but this was changed for the final aircraft in favor of a rear hinged door. This helps funnel air into the engine and improves pressure recovery on short takeoffs where the F-35B does not take off vertically, instead using the lift fan and directional thrust of the rear nozzle to take off on extremely short runways. The way this aircraft transforms to perform vertical landing and short takeoffs is astounding. It's the closest thing to a transformer we have ever created. When the time comes, a clutch linking the extended driveshaft of the F-35's engine begins to transfer 29,000 horsepower to the bevel gear of the lift fan, spinning the contra-rotating lift fan. Simultaneously, gears begin to rotate in the rear exhaust nozzle. The mechanics of this nozzle are another wonder to behold, called the 3-bearing swivel nozzle. It is composed of 3 airtight segments, cut at angles relative to one another. For we can change the shape of the nozzle by rotating these angled pieces separately. These 3 pieces rotate together to smoothly transition thrust downwards, but it's slightly easier to understand how it works by seeing what happens when we rotate segments individually. Rotating the central piece can take the nozzle from a 0-degree turn to 45 degrees. This position is used for short takeoffs, splitting the engine's power between thrust and lift. This mode is just as impressive as vertical takeoffs, allowing the plane to operate from shorter amphibious assault ships like the USS Makin Island, a ship just 258 meters long. Its minimum takeoff distance decreases even further with the aid of a ski jump, a ramp that has been added to smaller amphibious assault ships. Watching the F-35 take off over such short distances is incredible. In this clip, we can see the rear nozzle quickly adjusting its angle of thrust in sync with the rear elevators to adjust the pitch of the plane to ensure a safe takeoff. For a vertical landing, the final nozzle segment can rotate to provide the full 90-degree turn. The first nozzle segment can rotate to move the nozzle side to side, but here it's needed to ensure that the thrust doesn't move sideways as the nozzle transitions. As we saw when we rotate the segments individually, they move in an arc that would cause the F-35 to spin out of control. This mechanism also allows the F-35 to smoothly transition from cruise to vertical flight and from vertical flight to cruise when needed. There are additional control mechanisms to ensure this precarious balancing act does not go wrong. Bleed air from the main engine bypass is siphoned to two roll nozzles located on each wing, providing thrust far away from the plane's center of pressure to control roll. There are also guide vanes located underneath the lift fan. This can adjust the outlet area to adjust the performance of the lift van, but also control the thrust of the lift fan from 5 degrees forward to 42 degrees backward. With computer-assisted control of these control mechanisms, the F-35 is remarkably stable compared to its predecessor, the AV-8B Harrier, allowing the single engine of the F-35 to hover on two columns of air. To do this, the F-35's engine, the F-135, developed from the F-119 engine of the F-22 Raptor, had to be incredibly powerful. The F-22 Raptor is a twin-engined fighter, giving it plenty of excess power to pull off incredible maneuvers. The F-35 only has one engine and needs to squeeze out all the power it can get to perform a vertical landing. Where the F-22's engine can generate 156 kilonewtons of thrust, the F-35's can generate 191. The F-35's engine has a much larger fan and bypass ducting, giving it twice the bypass ratio of its F-22 counterpart, providing the F-35 with a more efficient engine for cruise, but also a much higher mass flow rate for higher thrust. However, this does come with some drawbacks. Air that travels around the engine core completely avoids the combustion chamber and thus misses out on the acceleration generated here, reducing the exhaust velocity. This reduces the top speed of the plane. The max speed of the F-35 is 1.6 Mach, and while it's the first plane capable of vertical flight and supersonic flight, the F-22 can fly at 2.2 machine. The F-35 was optimized for loiter time, not speed. However, all that extra weight needed for vertical takeoff seriously hampers that ideology. The lift fan module weighs 1.2 tons weight. That does nothing in normal flight and requires more fuel to carry, and to make matters worse, that space is used for an internal fuel tank for its variants. Making the lift fan as light as possible was pertinent to making the F-35 be viable in the battlefield. The fact it only weighs 1.2 tons is astounding. It contains two counter-rotating titanium blisks, blisk meaning the blades and disc are all one single piece instead of the traditional alternative of creating a disc and attaching blades through dovetail connections. This improves efficiency and eliminates a potential site of failure in the connection. This is an astounding feat of manufacturing, and the first stage fan takes it even further. The first stage blades are hollow to save weight. Where the F-35B truly comes into its own, however, is in its modern suite of sensors and computers all feeding into this. The heads-up display incorporated into the pilot's helmet. Traditional heads-up displays like those of the F-16 are incorporated into a panel in the cockpit, a panel which the pilot cannot see when scanning their environment. Situational awareness is everything in the heat of combat, and this helmet does everything it can to keep the pilot informed, even giving them X-ray vision and night vision information from a suite of sensors around the plane feed into a central computer, where it is processed and displayed through a projector inside the helmet. Inside this transparent faceted box underneath the aircraft is a suite of sensors. Those are not your typical windows. These windows are made from a notoriously expensive gemstone, sapphire, one of the few materials that is both hard and durable but also transparent to a broad range of electromagnetic wavelengths, from the ultraviolet to infrared. However, the radar antenna hidden inside the nose of the F-35 is the most important part of this electronic system. This is a scanned array radar that works very differently to traditional mechanical radar. Phased array antennas have hundreds of tiny antennas. We can see metal plates set in rows in the F-35 phase array antenna. The metal plates have slots cut into them, and each and every one of these slots is an antenna. 1,600 in total. This allows the phase array antenna to steer its radar using constructive and destructive interference. If two antennas release two radar waves at the exact same time with their peaks and troughs line up, it will result in constructive interference, increasing the amplitude of the radio wave. However, if the radio waves are set 180 degrees out of phase, matching the peak to troughs, it will result in complete destructive interference, canceling out the wave completely. This is how noise-canceling earphones work. They listen to the background noise and then release a canceling sound wave to create silence. The phased array antenna uses this phenomenon to steer the radio waves, preventing the radar from becoming a giant beacon leading enemies straight to it. Traditional phase array antennas are passive, meaning every antenna in the array is driven by a single transmitter and receiver. This would mean it can only point in one direction, and if it encountered two enemy planes flying side by side, and they split up, the passive phase array antenna would no longer be able to track both of them. However, the F-35's phase antenna is an active phased array, meaning each and every one of these antennas is an individually driven transmitter and receiver, meaning the F-35 can track multiple targets at once with zero moving parts. The nose cones hiding these antennas need to be transparent to radar waves and are usually made from glass fiber composites. As a result, this transparency causes issues for the plane's radar return signature, as an antenna like this will reflect signals. This was a much bigger issue for mechanical radar dishes that needed to point at the enemy to keep track of them. The phased array can point towards multiple targets while staying in a single position, and this is why it is pointed skywards to bounce incoming radar to space. The phased array antenna also acts as the plane's communication antenna, and this is critical to the F-35's battle doctrine. The F-35 excels in the battlefield because of its networking abilities. Relaying information between its squadron, this is a huge amount of data to transfer between aircraft and allies on the surface, and requires a high data transfer speed. However, communication comes with one glaring problem. It announces your presence to anyone listening. It is vital that stealth planes can communicate with each other securely, and the active phase array antenna facilitates this. The F-35 uses the latest data link system, called MADL, improving on the experiences learned with the F-22, allowing the F-35 to quickly share data securely from individual F-35s and ground-based systems. This information is then sorted and presented to the pilot in their heads-up display right in front of their eyes, giving them unparalleled situational awareness. No need to communicate with their wingmates. If there is an adversary underneath them, the planes communicate and feed that data right into the helmet, allowing the pilot to look underneath the plane and see the location of the adversary themselves. This is the true strength of the F-35B. It is a networked hive-mind stealth fighter, capable of taking off from a ship a fraction of the size of an aircraft carrier and returning while hovering in the sky like a helicopter. It's one of the most remarkable pieces of military technology ever created. The F-35 has borrowed many lessons learned from planes like the F-117 Nighthawk and B-2, planes that we have not made documentaries about yet, but our friends over at Mustard have. Their B-2 documentary is 20 minutes of beautifully crafted story filled with stylish 3D renders. If you like this video, you will definitely love these originals. You can get access to them by signing up with the link in the description. You can sign up directly to Nebula for just $4 a month or $40 a year. An incredibly good price to help us build the best creator-owned streaming platform in the world. Or you can use the incredible cost-saving hack of signing up to the Nebula and CuriosityStream bundle and get both streaming services for just $14.79 a year, getting access to all of CuriosityStream's award-winning documentaries and Nebula's amazing and ever-growing catalog. Nebula is a game-changing platform. We gathered all our favorite YouTube creators in one place to give us the power of a collective, funding our best ideas for documentaries like our Battle of Britain and Logistics of D-Day series, Real Science's Becoming Human series. We even funded Patrick Willems' feature-length film that I feature in a scene alongside Darren Aronofsky. That would not be possible on YouTube. We also upload early and ad-free on Nebula, giving you early access to Sam from Wendover and I's antics on Jet Lag the Game, along with exclusive behind-the-scenes videos, like the Layover After Show and our extended interview with David Kirtley from Hellion. We have many more documentary shoots planned for this year with fascinating companies, and we will be releasing behind-the-scenes footage for them all. You get all this while helping us build a platform that unlocks our